Another gas law, Avogadro's law. Where have we heard that name before? The number, that number, Avogadro's number, yes. And it was Avogadro's work with gases that gave rise to Avogadro's number and the concept of the mole. Boyle's law and Charles' law that we've been talking about have been relating pressure, volume, and temperature, and we've always said the amount of gas is staying the same. Well, what if the amount of gas changes? That's what Avogadro did. So he changed the amount of gas and looked at the volume. And this makes sense to us that if you put more gas in, the volume gets larger, right? What may not be obvious is that the volume is related to the number of moles of the gas. Not the mass of the gas, but the number of moles. So he measured volume at constant temperature and pressure while varying the number of moles, the number of particles. The volume depends on the number of particles. It increases linearly. And Avogadro was the first one to state this. It's kind of interesting. He was born the year that our country was born, 1776. So Avogadro's law states that the volume of a gas and the amount of gas in moles are directly proportional. And the variable we use to represent moles is the letter N. I don't know why. You might think it should be M, but M is always mass. So this makes sense. Here's a little guy blowing into a balloon. You put more air into the balloon gets bigger, right? So we can use Avogadro's law to do gas calculations. Now there's something missing on the slide, which is, how do they say it? I think they say it, V1 over N1 equals V2 over N2. I forgot to put the actual mathematical statement of Avogadro's law in this slide, so you might want to write that in. So here's a problem. A 4.8 liter sample of helium gas contains 0.22 moles of helium. How many additional moles of helium gas must be added to the sample to obtain a volume of 6.4 liters? So this could be a practical problem. It's a kind of a stretch, but you have this balloon, say, and it has this volume, and you need it to be a certain larger volume. And you need to know, well, how much more gas should I put in there to get it to be this volume? So what do we have here? Well, we're going to make a table again, because that's what we do with gas laws. 1 and 2. First number we come to, 4.8 liters. What quantity is that? That's a volume. It doesn't say it's volume, but we know that liter is a unit of volume. Contains 0.22 moles. So we'll write that down, 0.22 moles. And we just learned that the letter we use for moles is lowercase n. How many additional moles? Volume of 6.4. So there's the next number. So volume, we're going to put it in the volume column. Now when we look at our table, we have a blank. That's what we can find using Avogadro's law. That would be N2. Is N2 the answer to this question? No. This is kind of a tricky question. It's asking how many additional moles must be added. What is N2 giving us? The total number of moles, right? This is the moles of gas in that sample when the volume is 6.4 liters. How could we figure out how many moles we had to add? We have to subtract what we initially had. So we have to do a little bit of thinking here. But we do need to calculate N. So let's do that. N2. So our equation is V1 over N1 equals V2 over N2. So identify the thing you're solving for. it's N2. If you're good with algebra, just rearrange it and be done with it. I'll talk to the rest of the class, which is, I'm guessing, most of you. What do we need to do to this to rearrange it? What should we do first? Cross multiply. Get rid of those pesky fractions. They mess us up. So top of one side times the bottom of the other. So V1 times N2 equals the bottom of the first side times the top of the other side. N1 V2. Again, if this is not making sense to you, please talk to me sometime during lab today. I can explain it to you. We can get to that aha moment where you go, oh, that's easy. Because once you understand it, it is. Until then, not so much. So we're still looking for N2. So we got rid of the fractions. Now what do? We divide. We're going to divide by V1 to get rid of that. See, here we have N2. That's not a good color for the pointer. Really like the green arrow the best. There we go. There's N2. It's multiplied by V1. We need to get rid of that. So we divide by V1 and it cancels out. If we do that to one side of the equation, we have to be fair and do it to the other side. So the equation we come up with is N2 equals N1 V2 over V1. Then we bring our numbers over from the table where they're all arranged and clearly labeled. N1 is 0.22 moles. And that's multiplied by V2, 6.4 liters. And then we're going to divide by V1, which is 4.8 liters. So we find that the total number of moles of gas in the container or the sample is 0.22 times 6.4 divided by 4.8, which is 0.293333333333 for forever. All of the numbers that were given in the problem have 2 sig figs. So we'll round that off to 2 sig figs. The unit is moles. That's the total number of moles. The question's asking, how many do we have to add? We started with 0.22. How many do we need to add to get to 0.29? So we do subtraction there. I'll do it up here. So 0.29, what we want to end up with, and we're going to subtract what we started with, and we're going to end up with 0.07 moles. That's what we have to add. Any questions? They will do things like this to you in the homework. They'll make you convert units in the homework. Most of these have been real nice. They've given us the volume in liters for both of them. And here we needed moles, so they gave us moles. They could give us a mass here and make us convert to moles. Yeah. They could give us milliliters for one and liters for the other. So just be prepared for that. We learned how to do that, though. Question?
I just didn't understand how you do to subtract them. Can you just explain why it says must be added?
Right. How did I know to subtract them? So I'm looking at this question. How many additional moles of helium gas must be added to the sample? So this is where it's helpful to picture what's going on. So I'm going to, let's see, I think I can do this. Yes. So let's draw a picture. So here we've got a container of gas. And it's 4.8 liters and it's 0.22 moles. And I want that gas to occupy a larger volume, this is not to scale, of 6.4 liters. So in order to do that, the pressure and the temperature are being assumed to stay constant. I have to pump some more, well, let's move that over. I have to pump some gas into, maybe I'm using a bicycle pump. I have to pump some gas in there to increase the amount of gas. The question is not saying how many moles are in the sample if the volume is 6.4. It's saying how many additional moles must be added. So how many additional moles must be added? And then when we did the problem with the equation, what we're solving for, N2, is the number of moles that are in the container. But the question's adding how much do you have to add? So it's reading the question, and that's why it's important to read the question more than once. Because it's very common to read through a question and you just kind of skim it and you think you know what they're asking. And you go and solve that and then you put the answer into Mastering Chemistry and it's wrong. Then you go back and read it again and you're, oh, I missed that part. Does that help?
Yeah.
And the tricky thing about stuff like this is there's so many possibilities of little variations that I can't teach you a method to help you with all of them. And so that's where some, I guess you could call it common sense comes in, and just reading the question and thinking about it, maybe actually drawing pictures. If you need to do that, go ahead. Or maybe, I've gotten good at drawing pictures in my head. I imagine what's going on. Just thinking about it. Any other questions?